Meteorology Lab students, welcome back. Lab number 2 here. So what we're going to do today is we're going to look at the vertical structure of the atmosphere. We're going to look at different ways that we can think of the layers of the atmosphere. And other things we're going to look at is just going from the surface up, what changes about the atmosphere? How are things different from the surface, middle part, upper parts of the atmosphere? Because it's not continuous, all the same in terms of the characteristics of the atmosphere, in terms of the things that we can measure about the atmosphere. They vary from the surface all the way to the very top part of the atmosphere. Two main things we're going to look at today in terms of the atmosphere and its layering, or how it changes vertically. One is pressure, how pressure changes with height, and the other is temperature, how temperature changes with height. So those are going to be two really important ways for us to look at changes in the atmosphere as we go up. A couple little diagrams here just to show you some of the layers of the atmosphere, some of the things that we can associate with the atmosphere, or this layering where we find certain things like Space Shuttle, Hubble Telescope, things like that. So a couple of diagrams, SR-71, cool plane there. So just a couple of different ways that we can think of or look at the layering. So we'll start with pressure, and pressure we can think of as the weight of the atmosphere above a certain point. So if you picture where you're standing, that column of air that extends all the way to the top of the atmosphere, that has a certain amount of weight, and that weight we can think of as pressure, and it pushes on the Earth's surface. Now, it's sometimes weird for us to really think about the atmosphere as having a lot of weight or a lot of pressure, because we move so easily through it, because it is low density. But there is a weight to that, right? The atmosphere has mass, and with gravity it's going to have weight. And we can measure that force on the Earth's surface as pressure. And it turns out pressure and changes in pressure from one location to another on the Earth's surface are really important in terms of understanding weather, how weather is going to change, really important in terms of forecasting weather, things like that. So you cannot underestimate how important pressure is in terms of understanding weather on the surface. Now, today what we're going to look at is how does pressure change as we go up. And so let's start then at the surface. And at the surface, our average standard pressure is going to be what we call 1013.25 millibars. Millibars is just a unit we use to measure pressure in meteorology. Some of you might be more familiar with inches of mercury, or inches as it's sometimes referred to as. 29.92 inches of mercury is the standard atmospheric average pressure at sea level. Now, when we talk about that, does that mean that every single day it's this pressure at sea level? No, just that is the average, but it can vary any given day, any given location in terms of what we find at sea level. So just a couple other little measurements here. But what I really wanted to get to in terms of the lab today was this rule of thumb here, and that is we are going to lose half of our pressure for every 5.6 kilometers that we gain in altitude. It's about 3.5 miles or so that we go up. So in other words, if you go up 5.6 kilometers in the atmosphere, you're going to lose half your pressure. And go up another 5.6 kilometers, you're going to lose half that pressure. You keep losing half your pressure as you go up every 5.6 kilometers. And so what you end up with then is a non-linear relationship between pressure and height. So notice we have 1,000 millibars here, and we'll often, it depends on the exercise, but we'll often round off our surface pressure to 1,000 millibars rather than 1013.25. It just depends on the exercise we're doing. But that's a pretty good way to round off, and it makes sometimes some of the calculations we do a little easier. So 1,000 millibars here, and you go up this far, and you lose half your pressure. And so you go from 1,000 to 500. Go up that same distance again, you're going to lose half your pressure from 500 to 250. And so again, you lose that pressure as you go up, because as you go up, there's less pressure, there's less of the atmosphere above you. And so as a result, there's less weight or pressure. So for our exercise today, in our lab, we start off with this question, where we look at this change in pressure. And so I give you a couple of these to start with, and let me just show you how we kind of do that. So at sea level, we have 100% of our pressure, we're at 1,000 millibars. if we go up 5.6 kilometers, we're going to lose half that pressure. So we're going to have 50% of our pressure. Half of 1,000 is, correct, 500. 500 millibars. Now, we're going to go from 5.6 kilometers to 11.2. That's another 5.6 kilometers. So in other words, if you add 5.6 kilometers to 5.6 kilometers, you're going to get 11.2 kilometers. And so half of 50 is 25, and half of 500 is 250 millibars. So every time you go up here, you're gaining 5.6 kilometers in altitude. You're going to lose half your pressure every time you go up. So you're going to fill out this table here. And then when you fill that out, you're going to plot that data on this graph here. So we have pressure here, again, starting at 1,000 millibars here all the way down to 0, and our height here in kilometers. So you're going to have to estimate roughly where 5.6 kilometers is, plot 500 there, go up another 5.6 kilometers, 250, and you're going to end up with a graph that is non-linear. It's going to have a curve to it. Your graph should, and again, I'm not going to plot the points here, but just vaguely speaking, your graph should look something like that. So it's not going to be a straight line, it's going to be a curved line. Again, a non-linear relationship. And again, you have your key to help you figure that out. Now, there are other ways that we can calculate pressure. So, our rule of thumb of losing half our pressure every 5.6 kilometers is great, especially if you're at that 5.6 kilometers. But let's say you want to know what the pressure is going to be at 1 kilometer or 5 kilometers instead of 5.6. We can estimate that based on our standard pressure loss. And to do that, we use this little formula here. So we start off with 1013.25. We're going to multiply it by 0.5 to the x divided by 5.6 kilometers, where x is the altitude in kilometers. So for example, if we wanted to know what is the standard pressure at 2 kilometers, the first thing we do is we plug x into here. So we take 2 divided by 5.6, that's going to give us 0.3571. Then we take 0.5 to the power of 0.3571. Now how you do this can really depend on your calculator, but most calculators have an x to the y function, so you can take, for example, 0.5 x to the y, 0.3574, and you should get an answer of 0.7807. And again, that x to the y looks like this on this particular calculator here, but most calculators have that function. And so then once we get that part of our equation done, we simply then multiply 1013.25 times that number that we got here, and the end answer is 791.0 millibars. So what that tells us is at 2 kilometers height, we should expect the pressure to be 791.0 millibars, again, based on our standard pressure reduction. So that's how you do those calculations, and there's a table here where I have you guys work out the pressure for a variety of locations. So Badwater, Death Valley, sea level, Walnut, et cetera, et cetera. All right, so the next thing I want to jump to is just looking at the thermal structure of the atmosphere. So how does the temperature change as you go up in the atmosphere? Well, it turns out that the temperature profile is also very complicated. So what you see here is temperature along the bottom, and then height here in miles, height here in kilometers, and the yellow line is your temperature trend. And it's kind of surprising because if you look at this, it zigzags back and forth. So temperature decreases, it increases, decreases, it increases as you go up. And that's surprising for a lot of people to realize. Most people just assume the temperature decreases from the surface all the way to space. And it doesn't. What we're going to focus in on really today is this bottom part here. bottom layer here is called the troposphere, then the boundary is called the tropopause, and then the layer above is called the stratosphere. So what we're going to look at today and focus on is looking at data and trying to determine where the tropopause is. And the way to determine the tropopause is when the overall trend of decreasing temperature stops. So you notice here, temperature is decreasing, 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 and it stops decreasing here. Now, it could be that the rate of decrease just slows down. It could be constant. It could increase a little bit. But basically, that pretty constant rate of temperature decrease suddenly changes dramatically. And that is where your tropopause is. And that's what we're really going to focus in on again today. So to help us with this, we have what's called radiosonde data. This is basically data collected by a weather balloon that, so it's a big gigantic balloon with an instrument package attached to it. That balloon is let go into the atmosphere. It rises up, and as the balloon rises up, it is taking measurements of the atmosphere. Our main interest is going to be temperature, but I have a few exercises for you guys to do where you just get used to looking at the data. But it's a ton of data you guys have, lots of data sheets. Little hint for you guys, when you're answering questions, always make sure you're looking at the correct data sheet. There's one from Key West, there's one from Denver, there's one from Fairbanks, Alaska, and then two from Topeka, Kansas. Okay, so make sure you're looking at the right data set when you're answering specific questions today. So, but again, so the idea again is that the balloon goes up and the balloon makes these measurements as it goes up. And again, our main interest today is going to be that temperature measurement. So how does temperature change as the balloon goes up? And when does the balloon transition from the troposphere to the stratosphere? When does it pass that tropopause? That's what we want to be able to try to identify in our data. Now, there's a lot of data here. So what I did is I simplified and kind of rounded off the data to make it easier for us to graph. And that's what these tables are here. So basically what you'll see is height here in 1,000-meter intervals, just to make it easier to plot on our graph. And then this is the temperature data here for each of those 1,000-meter intervals. Now you will see a couple of cases where we have these dashed lines. That indicates that there's no data recorded at that height. Just skip it. Just don't worry about it. Sometimes that happens. Sometimes there's malfunctions with data, or simply the data was not recorded close enough to that 1,000-meter interval for us to kind of round off and use for our data sets. So what you're going to do is you're going to plot your Key West data, your Denver data, and your Fairbanks data on the graph provided here. Ideally, if you have colored pencils, you use different colored pencil for each one, but either way, just make sure you label each line so I know which one is Key West, I know which one is Denver, I know which one is Fairbanks. You're also going to plot the environmental lapse rate on here. That's a previous question I didn't go over, but you're also going to plot that on here. So make sure all your lines are plotted. And let me just sort of, again, give you a rough idea of what you should expect. So you're going to plot your data, and let's say your data looks something like this, right? And so temperature is decreasing, 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 decreasing. But notice right about in here, that overall trend in temperature decreasing starts to change dramatically. You know, really, if you were to kind of summarize it very crudely, right? Temperature sort of decreasing here, but very different here. And where you have that transition between these two trends, that's going to be your tropopause. Okay, so you're looking at your tropopause there. So again, overall decreasing here, change here. Now, you're going to expect the tropopause fairly high up in the atmosphere. You're not going to see it 1,000 to 2,000 meters up. It's going to be, 8, 9, 10, 12, 15, 16, 17, 18,000 meters, something like that. Right? It's much higher up. So if you see something at the surface or close to the surface within a few thousand meters, that's not it. It's got to be much higher up. So in this generic example I've done here, we're looking at probably maybe close to 12,000 meters, 11,500 meters, something like that is where the tropopause would be in this particular generic example. But you're going to plot that data, again, your temperature data, your height in meters here, and you're going to have a bunch of lines that look vaguely like this. But they're not all going to be the same. Your Key West line is going to look different than your Denver line. That's going to look different than your Fairbanks line. Those are three different locations. So you want to think about how does location influence that? Why is Key West different than Fairbanks, different than Denver? That's one of the key parts to understanding this, this lab. So, quick rundown, I know, but hopefully just hitting some of the high points for you guys when it comes to this week's lab. Good luck. Remember, again, go through the key to help you answer those questions. One more little hint, too. In your post-lab, what you're looking at in the post-lab is not data from different locations. It's from the same location, Topeka, Kansas, but the difference there is the date. One data set is from January, another one is from July. Or in other words, one is from winter, one is from summer. Hint, hint, hint. Think how that might influence the height of your tropopause. All right, any questions, let me know. Hope it goes well. I'll see you next time.